Today we're going to talk about Kepler's laws of planetary motion. Johannes Kepler developed three laws which describe the motion of the planets across the sky. Kepler's first law describes the shape of a planet's orbit. It's sometimes referred to as the law of ellipses. It says basically that planets move in elliptical orbits. The Sun is at one focus and the planet orbits around on the outside. Not all ellipses are the same. Some are flatter than others. It's eccentricity that tells us how flat the ellipse actually is. Eccentricity ranges anywhere from 0 to 1. A circle is a special case of an ellipse where both foci are at the same spot. The eccentricity of a circle is 0. Let's look at Mercury's orbit as an example. On the left we have the Sun at one foci, and on the right we have what's called an empty focus, with Mercury traveling around on the outside. To draw an ellipse, imagine we have a looped piece of string, and we had two push pins here at each focus, and we were to trace with a pencil, stretch the string out as far as we can and trace out that shape. That would draw an ellipse. For the eccentricity, the more eccentric an orbit becomes, the flatter it becomes. And at 0, we get a circular orbit. The orbit of Venus is nearly a perfect circle. Kepler's second law relates to the speed of a planet in orbit. It's also known as the law of areas. It says an imaginary line that connects a planet to the Sun sweeps out equal areas in equal times. So what does that have to do with speed? In a given month, the planet cuts pieces of pie that have the same area, but the shape of the pie pieces can vary greatly. The crust of one piece can be much longer than another. This is a result of the speed of the planet changing. When the planet is closer to the Sun, it travels a greater distance in the same time, so it's moving faster. When it's further away, it travels a shorter distance in the same amount of time, so it's moving slower. The speed in the circular orbit will be constant. Let's use Mercury's orbit as an example. If we were to sweep a segment when Mercury is close to the Sun, and a segment when Mercury is far away, when it's closer to the Sun, Mercury is traveling a much greater distance in the same time period than it is when it's further away. So over here on the left, Mercury has to be traveling faster than over here on the right. And if we sweep out pi pieces for all 12 months of Mercury's orbit, all these pieces have the same area. And you can see that when it's closer to the Sun, the pi pieces the crust is longer, so it's going to travel faster. When it's further away, the crust is shorter, so it's going to travel slower. For Venus, because its orbit is nearly circular, all the pi pieces not only have the same area, but their crust lengths are almost all the same. So as a result, the speed of Venus in its orbit stays pretty constant. Kepler's third law ties the whole solar system together. It's also known as the law of periods or the law of harmonies. It says the square of the period of an orbit is proportional to the cube of the radius. So what does that mean? It means the ratio of period squared to radius cubed is equal to a constant. And that constant is the same for every planet in the solar system. If we plot radius cubed versus period squared, we get a linear relationship. Every planet that revolves around the Sun falls along this line. If we know an object's period, we know how far it is from the Sun. Let's start with Earth as an example. The average Sun to Earth distance is what we call 1 astronomical unit. So going forward, we'll compare all the other planets, their Sun to that planet distance, what we call the semi-major axis, we'll compare that to Earth, so we'll do it in terms of astronomical units. And then the period for one revolution for Earth, we'll just call 1 year. So if we look down at this table here, now they have their period on the vertical axis versus where we had the radius, but it works out the same either way. So the period of Earth is 1 year, so 1 squared, right? And then we take the cubed root of 1 squared would give us 1, right? So if we picked any other planet for the solar system, so we pick Jupiter or Saturn rather, all right? From astronomical data, we can see that Saturn has an orbital period of 29.5 Earth years. So if we were to square 29.5, then take the cube root, it would give us 9.54. So that tells us that Saturn is 9.5 times further from the Sun than Earth. It's 9.5 astronomical units, and you can see that it falls along this line. Neptune has an orbital period of 165 Earth years. 165 squared, we take the cube root, gives us 30.1 astronomical units, and again you can see it falls along this line. Every planet falls along this line. Mercury, 0.241 Earth years for its orbital period, 0.241 squared, and we take the cube root, gives us 0.387 astronomical units. Kepler's laws of planetary motion provide only a description of the patterns he discovered studying the orbit of Mars. It wasn't until Newton, many years later, that these laws were shown to be a result of the gravitational force that exists between any two objects.